So the thing you have to remember is that transient response for second order systems are going to be damped sinusoids. Transient response. Sinusoids. And unless so that being a ramp input, an impulse input, a step input, they're damped sinusoids. Unless we have, well, no, the transient is always going to be like this. So, but the steady response is going to be, it's always going to tend to zero angle of attack, or something. It's not going to change with time. It's going to be permanent. For example, in a step input, it can be, it can tend to a certain angle of attack, which isn't common, because as we discussed before, we're not going to find many step inputs. We could actually imagine this could be a real case of a step input. If we had the nozzle slightly misaligned and the thrust wasn't aligned to the roll axis, we would have a permanent moment here caused by the thrust misalignment. And this would cause the rocket to go to fly at a certain angle of attack, but not a crosswind. Crosswind wouldn't cause a step input. Anyways, if we have a step input, an impulse input, it's always going to tend to stop the oscillation. However, if we have a sinusoidal input, the transient is going to be something that we're not interested in studying it. So maybe it's going to be, before looking at the response, what is sinusoidal input? It means that a force, so it would mean like a moment described, external moment described, like a permanent sinusoid. Alright. There can be cases of a sinusoidal input, and probably the only case I can think of is the rocket starting to roll, and then any kind of external moment that before it could have been a step. For example, this thrust misalignment. Well, it's going to be sinusoid right now, because when the rocket rotates a bit, then this moment. Well, the moment is gonna change like a sinusoid in time. So actually, we're gonna see that the steady response to sinusoids are gonna be of great interest, because we're gonna see that they are pretty dangerous and they can cause resonance, as we're gonna see. So the sinusoidal input. If we have a sinusoidal input, the rocket isn't going to stabilize. It's going to do something random at the beginning. So if we hit the rocket with a sinusoidal input, it's going to do something random at the beginning. I don't care. We don't care about the transient response on a sinusoidal input. But when it finally when the transient dies out, alpha will not stabilize. It will start oscillating, at the same angular frequency as the external forcing moment. Alright, it's not going to dampen out. Then what about the amplitude of this sinusoid? So maybe we have the amplitude of the external moment, which can be whatever you want it to be. But how does this amplitude translate to this amplitude? Well, this is when you need the Bode. I don't know how it's pronounced in English. I'll just call it the Bode diagram. If you're familiar with control theory, you know what a Bode diagram is. Again, I'm not gonna explain what it is. If you don't know what it is, I just recommend you to check text control theory textbook. Maybe I recommended before Rata, or just Google. You can learn anything on internet. I've learned everything just searching and reading and buying books. So if you don't know what a Bode diagram is, I recommend you to check this so you can understand how the sinusoidal response is going to look like. Okay, now I'm going to suppose you're familiar with it, so I'm just gonna refresh you how the Bode diagram is going to look like. So this is a frequency of the response and of the input. Remember that the frequency is going to be of the response is going to be the same as the input. Yeah, I didn't put never mind. Yeah, just remember this is the same for the oscillation of alpha as for the oscillation of our forcing moment. So remember that for a second order system, second order undamped system, this is going to look something like this. The Bode diagram is going to look something like this. Remember that on this axis we have the gain, which is normally the units we usually use is decibels, but the gain, just recall, is the let's say the amplitude of the alpha oscillations compared to the amplitude of the forcing oscillations. So it's the relationship between this amplitude and this amplitude. Okay. Alright, so remember that for a second order undamped system, the Bode diagram is going to look something like this. Well, normally we have plotted here the log angular velocity, but it's going to look like this. Okay. I'm just going to do a quick recap of what this means. Around here, not exactly here, but around here, is the natural frequency, okay? So, what this point means, okay, is a sinusoidal input of angular frequency W sub 0. Okay, so if we have this kind of sinusoidal input, so sinusoidal input would be something like A times sine. In this case, we're taking this. Then the output is going to be of similar amplitude, or it's going to be same order of magnitude of the external force. Okay, because the gain is 0 decibels here. Okay. What happens if we have, so this will be like a slow input, like a slow frequency input. If we hit the rocket at just the natural frequency of our rocket, which is going to be a higher frequency than this, if we hit the rocket with this frequency, the gain here is going to explode, because our damping ratio, remember that we're talking about something lower than 0.1. And if you take the gain at around these frequencies, this is going to explode. This is going to be, I don't know, for such low frequencies, for such low damping ratios, the gain is going to be enormous. So here, if we have the same amplitude of an external moment, imagine that for this frequency, the output was something like, I don't know, let's say angle of attack 2 degrees, okay, minus 2 degrees, and this of course is the same angular frequency, angular velocity as the external input. So if we hit the rocket with the same amplitude, so it's the same force but go at a faster frequency, okay, then the angle of attack is going to explode. It's going to be whatever. I don't care about the numbers. It's just gonna, the gain here is just gonna explode, right? What this means is we're hitting resonance here. This is resonance. And this, of course, we want to avoid. We want to avoid any kind of sinusoidal inputs that are of frequencies around the natural frequency of the rocket. When do we have sinusoidal inputs of a frequency, well, whatever angular, whatever frequency, when the rocket is rolling at this frequency, okay? If not, it's really strange to find an external input that, is a sinusoid. Unless we have the rocket rolling at, for example, this frequency, we're not going to have an external force of this sinusoid. So we're gonna have to avoid the rocket rolling at this frequency, because if not, it's just going to blow up. It's going to blow up. Like, no way you can avoid this resonance. It's always going to be here because the damping ratio is tiny for rockets. We saw that the damping was caused just by the oscillation, the induced velocity due to the oscillation, which is tiny. So for rockets, unfortunately, there's no way of going around the resonance. I don't care if you put ginormous fins. You're not going to get the damping ratio to 0.7 or 0.5, which is damping ratios at which there is no resonance. So if you had damping ratios of this, you wouldn't have this problem. Okay. but these damping ratios are unattainable. So we gotta look at another way. We just have to avoid spinning the rocket at these frequencies, because if not, any external force is going to turn into a sinusoid of this frequency, and when the transient is gone, it's just gonna blow up. There's no other way around. And what happens if we roll the rocket at higher frequencies than the reference zone? Well, you have negative gain. This means that if you have an external moment, this is really high frequency, of the same amplitude, of amplitude A, a negative gain means that you're gonna have a tiny response. This means that if we're rolling, this is safe zone. This is safe. This is safe, and this is kind of safe. Kind of safe. You'll see why it's kind of safe. Well, first of all, because we have here we have like negative gain. Here we don't have. We have zero gain, but yeah, over here we don't care about sinusoidal inputs. It's just gonna. The rocket isn't even gonna notice it. The rocket is like super stable over here. All right. But around here, yeah, we're gonna have to avoid it. So we wanna really know what this natural frequency of the rocket is if we want to avoid it. Okay. Because if not, well, yeah, it's gonna blow up.